Hi everybody, welcome to the first unit of grade 10 IB Math. The first unit is on what's called linear systems. So I'll do a little bit of an introduction here as to what linear systems are. Basically what a linear system is two or more linear equations. So we remember what a linear equation was from grade 9. A linear equation was y is equal to mx plus b. Basically a line on a graph. That's where linear comes from. And remember, linear equations don't always have to be written as y is equal to mx plus b. There's also the standard form, which was ax plus by is equal to c, where a, b, and c were numbers. So an example would be y is equal to 2x plus 5, and maybe 3x plus 4y is equal to 5, something like that. So these are linear equations, and what a linear system is two of them. This is a linear system. That's what we're going to be working with in the first chapter. Basically, what we want to do with a linear system is solve for the unknowns. So if you look at the equations that we have here, we have two unknowns. There'll always be two unknowns. We're going to have x, one here and one here, and we're going to have y, one here and one here. And there will most times only be one unique value of x and y that will balance both equations. And what does that mean? So let's go down and look at some examples here. So an example of a linear system, kind of like what I gave you above, but they could be written y is equal to 3x plus 5, and y is equal to negative 2x plus 9. Could be written like that. Like I said, you can have it in standard form. You might have 2x plus 3y is equal to 8. You might have 5x minus 2y is equal to 10. Or you can have it a mix between those ones. But basically, we're going to have linear equations. And remember, what a linear equation means is all the variables all have an exponent of 1. So when nothing's written there, they're linear. If it was a 2, it'd be something else. 3, something else. So each of these is a linear system. We have two unknowns. And in order to solve for the unknowns, x and y in this case, I need the two equations. So a linear system is two linear equations. Now, in this chapter, we're going to go through methods to solve them. So what does that mean to solve them? That means actually find out what x and y are. You've solved linear equations before, so you might have y is equal to, I don't know, y is equal to, let's say 3x is equal to 9. In grade 9, you solved these ones. And you would have said, well, I'm going to divide both sides by 3. I'm going to find out that x is equal to 3. And that was good. Now what we're going to do is we're going to have two unknowns we're going to solve for. We're not just solving for one. And we have three ways that we can do that. So each of our sections in our chapter 1 is going to go through a different way. So the first way, 1.1, is solve by graphing. You can imagine what that means. We're going to graph the two linear equations. We're going to look at 1.2, which is solve by substitution. Whoops. And 1.4, which is solving by elimination. So if you break these down, first one, solve by graphing, we're obviously going to be using a grid. The other two use algebra. We're going to substitute one equation into the other in order to solve it. And for elimination, we're going to eliminate one of the two equations that we have. Right? Because remember, a linear system is two linear equations. So each of these ways we're going to go through. So today we're going to look at the first one, solving by graphing. So 1.1, graphing linear systems. Solving a linear system with two variables graphically requires both lines to be plotted on the same set of axes, Once this is completed, we're going to find the point that simultaneously satisfies both equations. And that's going to be the spot where they intersect, right here. If you look, it has a coordinate. The x value is 3, and the y value is -1. So both of these equations that we have at the top have been graphed. Those are the two lines that we see. So I'm going to choose the first one here. And if you forgot how to graph, do a little bit of a recap here. Basically, what we do is we try to isolate y. And the way that I'm going to do that is I'm going to take 2x and move it over to the right side. When I do that, I'm going to get y on the left side is equal to, well, 2x went to the right side, becomes -2x plus 5. And when we graph that, you might remember that my b value is 5. That's my y-intercept. My m value is -2. That's my slope. And usually for slope, we write it as a fraction because I want to know what the rise is, and that's the number that's on top, rise, and the run. So let's go back and see this. So the y-intercept is 5. So if I look, y-intercept 5, that's right here. And the slope is -2, or -2/1. That means I'm going to rise -2, go down 2, and run 1. Go down 2, and run 1. And that's where that line comes from, that line that's decreasing from left to right. So this line here is technically y is equal to -2x plus 5. That's the first one. Let's have a look at the second one. Use a different color. So this second one, I'm going to try to isolate y again. So in this case, I have -y on the left side, and I have x on the left side. So what I'm going to do is I'm going to take the x and move it over to the right side. Remember, it's going to become negative. So my new equation is going to be -y, right? The coefficient on y is -1, so it's got to stay as -1, is equal to, well, now x has moved over. It becomes -x. And +4 is already there on the right side, so it remains as +4. Now, that's not in y is equal to mx plus b form, it's because it has -y. So what I'm going to do is divide everything by -1, because I want to change the sign so that I can get y is equal to -x divided by -1 is just x, and 4 divided by -1 is just -4. So that's my other equation that we've got. So it has a slope and b value, well, b value of -4, and a slope and m value of 1, because x is by itself. And if I wanted to graph that, I would start with my y-intercept, the b value of -4, and I would plot that. And my slope as 1, or I can write it as 1/1. Right? Any whole number can be written over 1, which means I'd rise 1, run 1. Rise 1, run 1. And I would draw a line through all those points, and that's how we get that second line there. So that second line is the line y is equal to x minus 4. I'll take off all this work here on the right, just so there's not too much on here so we're not confused. But that's the idea. We have our two equations, and I find out where they intersect. 3 and -1. So what's significant about 3 and -1? Well, 3 and -1 is the only point that I can plug into both of these equations that will make the left and right side balance. We say that satisfies the equation. So I'm just going to show you. So I'm going to be substituting in x is equal to 3 and y is equal to -1. So I'll take the first equation here. Go back, take the first one here. And I want to test this. 2x plus y is equal to 5. And I'm going to plug it in. 2 times 3 plus -1 should be equal to 5. And as I work my way through, I would get 6 plus -1, the same thing as subtracting 1, is equal to 5. And 5 is equal to 5. I like that. Both sides balance. 5 is indeed equal to 5. So that first equation works. We'll try that for the second one. So the second equation that we have is x minus y is equal to 4. And when I substitute in that point, 3 for x minus -1 for y should be equal to 4. I get 3. Subtracting a negative is the same as adding 1, which is 4. And we get 4 is equal to 4. I like that too, because 4 is indeed equal to 4. So that's my way of checking that I did everything correctly, that I graphed it right, because there should only be one point that makes both the first equation and the second equation balance. And in that case, the only point is 3 and -1. So you might say, well, what will happen if I choose a point that doesn't work out? Well, I'll take this off here. Oops. Take off the bottom piece here and the bottom piece there. And let's suppose we chose a different point. Take all this off here. Let's suppose we picked a point that was not where they met. Like, let's choose, I don't know, let's pick this point right here. 0 and -4. Suppose I got that as my answer. I made a mistake when I graphed and I got 0 and -4. What's going to happen when I check my answer? So I'm going to put in 0 for x and -4 for y. Well, let's try the first equation. So I would get 2 times 0 plus -4 should be equal to 5. I would get 0 plus a negative is like subtracting. 4 is equal to 5. -4 is not equal to 5. That's not right. So I know right there that I made a mistake somewhere. Let's see what happens when I plug it into the other one here. X, 0, take away, -4 is equal to 4. So the first number I get is 0. Subtracting a negative is the same thing as adding. And I get 4 is equal to 4. So I might say, wow, that one balances, but the one on the left didn't. So I knew there was a mistake. You might say, well, why did the one on the right balance? Why was this equation okay? Well, the point that we selected up at the top happened to be on that line, x minus y. Because remember, this one is x minus y is equal to 4. So basically what we're doing down at the bottom is checking, is this point on that line? So on the right, it said 4 is equal to 4. So yeah, that point that we selected is on that line. The one over here on the left did not work out because that point, 0 and -4, is not on the line 2x plus y is equal to 5. That's why it didn't balance. So that's what we do when we check. We make sure that we pick the right point. We didn't graph incorrectly. We didn't make a small mistake. So we do a check, and this is called a formal check. And that's how we check. So let's go through a full example here. Solve the linear system. Y is equal to, so I'm going to write this one out. Y is equal to 2x minus 8. And the other one is x plus y is equal to 7. So that first one, I should be able to graph because it's already in y is equal to mx plus b form. Maybe I'll use red for this one. I know that the m value is 2. Or I can write it as 2 over 1. And the b value is -8. So when I graph it, I'm going to put a dot for the b value, the -8, the y-intercept, right on the y line. The slope is 2, so I'm going to rise 2, run 1. And I'm going to rise 2, run 1. And I'm going to continue that pattern all along as many times as I like. And draw a line through those points. Take that off. Draw a line through those points to represent the line that we've just graphed. Now the second one that we have here. I'd like to put this into y is equal to mx plus b form. So in order to do that, I'm going to have to take this x and move it over to the right side. That's going to create a new equation. It's going to be y is equal to -x plus 7. So I want to graph that one. So I'm going to use a different color for that. So let's say the m value, the slope is -1. That's the coefficient that's on x. Or we can write it as -1 over 1. The b value is 7. So let's go and graph that. I'm going to start with the b value, the y-intercept of 7. My slope is -1 over 1. That means I'm going to go down 1, 1 to the right, put a dot. Down one, one to the right, and another dot. Down one, one to the right, another dot. And I continue that pattern all along until I have enough to put my ruler. And I draw a line. Whoops. Not a very good line, but I can draw a line through all those points. And I look for where they intersect. So in this case, I see that they intersect right here. The coordinates of that point are 5 and 2. So the solution to this system, the solution to this linear system is x is equal to 5 and y is equal to 2. That's my answer. I can express it as that way or as the point that we have over there on the right, 5 and 2. Both are fine. And if I wanted to check that, doesn't always ask it to check it, but I'll do it here. Suppose I wanted to check if that answer is correct. Well, I'm going to take the first equation. Y is equal to 2x minus 8. And I'm going to substitute in x is 5, y is 2. So 2 is equal to 2 times 5 minus 8. And when I put that into my calculator, I'm going to get 10 minus 8, which is 2. Makes sense for that one? And I'm going to try it in the other equation. The other equation is x plus y is equal to 7. When I plug in x is 5 plus y is 2 is equal to 7, I'm going to get 7 is equal to 7. Both are good. I know I did it correctly. If one of those didn't balance, I'd know that I did something wrong. I'd have to go back to how I graphed my line to make sure that that I did it correctly. All right, a couple more examples here. Example 2. Solve the linear system. 3x minus y is equal to 15. So I'll use blue for this one. So it's 3x minus y is equal to 15. So in this case, I'm going to isolate for y. So I'm going to bring 3 over to the right side. So I'm going to have negative y is equal to negative 3x plus 15. Because I brought 3x over to the right side. Negative y stays as negative y. Then I'm going to have to divide everything by negative 1. I'm going to get y is equal to 3x minus 15. So we might look at this and say, that's going to be difficult for us to graph because I don't have a y-intercept of negative 15. Right? My b value is negative 15. My m is equal to 3 over 1. So how else can I graph this one when it's not on the grid? Well, I can choose some points to see where they would be at certain values, and I can use the slope from there because technically if I went down to 9, 10, 11, 12, 13, 14, 15, I would have a dot here, and I know that it's a positive slope. So it's coming up in this direction, but I don't know exactly where. So I'm going to choose a number. Let's choose a number maybe like 3. Oops, maybe I shouldn't put that dot there, but 3. And I want to find out where my graph is at 3. So I would say, what is y when x is 3? This is kind of a test. So we're going to say y is equal to 9 minus 15. Y is equal to negative 6. So I know that my point is here at negative 6. So I don't always have to start at the y-intercept. Normally you would, if we can. However, our graph is off the grid, so I can't do that. Now from there, now that I have a point, I can use my slope to find some more points. I'm going to rise 3, 1, 2, 3, and run 1. Rise 1, 2, 3, and run 1. Rise 1, 2, 3, and run 1. Rise 1, 2, 3, and run 1. So now I have a bunch of dots that I can put my ruler up to, because really all we need is 2 or 3 dots, in order for us to put our ruler up to. Something like that, and something like this. So let's try the second one. Use red for this one. So our graph is negative x plus 2y is equal to negative 10. So what I'm going to do is I want to isolate for y. So I'm going to take x and bring it over to the other side. 2y is equal to, x becomes positive minus 10 when it goes to the right side. And I'm going to have to divide everything by 2. So that leaves us with y is equal to 1 over 2x minus 5. So that means I'm going to start with my b value, which is negative 5, and my slope, which is already a fraction, 1 over 2. Rise 1, run 2. So let's go about that. I'm going to put my y-intercept of negative 5, and I'm going to rise 1, and I'm going to run 2. Put a dot. Next, I'm going to rise 1, run 2, and put a dot. And I continue that pattern along. I already see where they intersect, but I'm going to draw my line. And I see that they intersect at that coordinate. We'll go back to blue for that. Right here at a coordinate of 4 and negative 3. So the solution to this system is x is equal to 4, y is equal to negative 3. And once again, we can check that. We can plug in 4 and negative 3 for x and y to see if they balance. So let's take that first equation and see. So the first one was, so I'm going to do my check down here. 3x minus y is equal to 15. I know x is equal to 4, so 3 times 4 minus negative 3 should be 15 if I did it correctly. 4 times 3 is 12. Subtracting a negative plus 3 is equal to 15. And we get 15 is equal to 15. That one's good. Equation 1, I like. Second one, negative x plus 2y is equal to negative 10. I know that we're a negative x, so negative 4 plus 2 times negative 3 should be equal to negative 10. Negative 4. Positive 2 times negative 3 is negative 6. Negative 10. And when I add the left side, it matches the right side. So I know that we did it correctly. And we're happy. So you notice that they're getting a little bit harder as we go along. So we've made that so that you start with easy ones and things get a little more difficult as we go along, but we follow the same process. So I'm going to go out graphing this one. So sometimes what you can do is decide on a color for each of them. So the first one I'm going to pick blue, second one we'll use red, and we'll see where they intersect. So this first one, a little different because there's a coefficient on top of each, variable. But same idea, I'm going to isolate y. I'm going to take 4x and move it to the right side. Is equal to negative 4x plus 16, and divide everything by 8. We're going to get y is equal to, now I have negative 4 over 8. I can reduce that fraction of negative 4 over 8. Right? Maybe I'll write it as negative 4 over 8 for now. But I know that 4 goes into both those numbers evenly. 4 goes into the top once, and 4 goes into the bottom twice. So really, 4 over 8 is the same thing as negative 1/2. And over on the right side, we have plus 16 divided by 8, which is positive 2. So we're going to about graphing that. I'm going to have b is equal to 2, and m is equal to negative 1/2. So the b value of 2, I'll put that on my graph. We know how to do that. Now, what happens when the slope is negative? Negative 1/2. Well, I can assign that negative either to the top or the bottom. It doesn't matter, but one or the other. Normally, we assign it to the top. So think of it as negative 1 over 2. So when I do my rise, I'm going to go down 1 and to the right 2. Usually assign it to the top. So here I'm going to go down 1 to the right 2, put a dot. Down 1 to the right 2, another dot, and I continue that pattern. I can continue it to the left too, so notice that because I'm going down and to the right, well, it's the same as going up and to the left. Up and to the left, up and to the left, and up and to the left. I end up with a line like so. Now we're going to do the same thing for the other one. We're going to have to rearrange for y. And we'll use red for that one. So this equation is 3x minus 2y is equal to 4. So same idea, I'm going to isolate for y. So I'm going to take 3x and move it to the right side. So I'm going to have negative 2y on the left is equal to negative 3x plus 4. You have to remember to keep this negative 2y. Doesn't just change sign because the other term went over there, because the coefficient on y is negative 2. I know it says subtract 2y, but subtracting 2y is down 2y. We're less 2y. And then from there, we're going to divide everything by negative 2. I'm going to get y is equal to, so we have a fraction of negative 3 over negative 2. So you might remember about a fraction. If the top and bottom are negative, really that's negative divided by negative. So that's actually a positive fraction. So it's positive 3 over 2 when you divide two negatives. And I can't reduce that one anymore. 3 over 2 is lowest terms. X, I have plus 4 divided by 2, which is negative 2. So now I'm going to plot that. I have a b value of negative 2. And I have a slope of positive 3 over 2, which is rise 3 and run 2. So I'm going to put that onto the grid. Negative 2. And I'm going to rise 3, run 2. Rise 1, 2, 3, run 2. Rise 1, 2, 3, run 2. Whoops, run 2. Rise 1, 2, 3, and run 2. And I can go in the opposite direction, right? Because I have gone up 3 and 2 to the right. Well, I can go the opposite. I can go down 3, 2 to the left, and I'd have a dot. Right, so you can do it in either direction. Doesn't matter. But we end up with a bunch of dots. As long as you have 3 dots, I should be able to make a line that looks something like this. And I can see where they intersect already. We'll use, I see that the intersection in this case is 2 and 1. I can write that as x is equal to 2, y is equal to 1. And that's our solution to our system. We solved it by graphing. And once again, you can check that by substituting to both equations, and they should balance, and they do in this case. You can test it if you like. Lastly, this one's a little bit different, but it puts it in perspective a little bit for what we're looking at. So this one is a little bit of a word problem. So it says, example 4, suppose you're choosing a hall to rent for a wedding. 2 banquet halls are considered. Hall A charges $1,000 fixed rate plus $40 per person. Hall B just charges $60 per person. So one way that we can do this when we have large numbers like this is to make a table of values if we like, or we can make an equation. So I'm going to show you how to do both. So let's suppose we need to use a table of values. So the one that's on the left, we're going to have 2 unknowns. The unknowns are the number of people that are going to the party, and C is the cost of the party. So for Hall A, this one over here will be Hall A. It says 1,000 fixed rate plus 40 per person. So if no people go, well, I still have to charge, or I'm still charged $1,000. So they had to book it. They had to hold the hall for me, but I ended up not having a party. For the next one, we have 25 people going. So that's really like 1,000 plus $40, because $40 per person, times 25 people. That's another 1,000. So the answer in this case is 2,000. For the next one, we'd have 1,000 plus $40 times 50 people, which is 2,000. And you can continue that all throughout. You might see a pattern happening here, but essentially it's going to work out to 2,000, 3,000, 4,000, and 5,000. You might have done that back in grade 9. So for the one over here on the right, which is Hall B, it says number of people that are attending. If it's 0, well, it costs 0 because there is no fixed fee. It's only $60 per person. But then the next one is 25 people at $60, so times 60 is 1,500. The next one, we have 50 people go, so 50 times $60 is 3,000. And you can continue that through, so 60 times 75 is 4,500. And lastly, 60 times 100 is 6,000. So I can go about graphing that. You could have tried to come up with the equation for it. So for Hall B, the equation would have been cost is equal to 1,000, that's that fixed rate, initial value, plus it was $40 per person. Maybe I'll call it P. Actually, I think we used N, so 40N. For Hall B, there was no initial fee, so 0 was the initial fee. So I can have 0 plus, but it was $60 a person. So I don't really need that 0 there, but just to show you that the initial fee was 0. So I can go about graphing this if we wanted to. I could say, well, my slope in this case is 40, right? The value that's with the variable. My slope for the second one is 60. It's the value with the variable. My y-intercept is the initial value, 1,000. For Hall B, my y value is the initial value, which is 0. So I can go about graphing it using that method too. It doesn't matter because you're going to end up with the same line at the bottom. And I know that you've covered some of this in grade 9. But let's just go about graphing these ones. What I can do is plot the points, 0 and 1,000, 25 and 2,000, and so on. Or I can use the slope and y-intercept in order to graph it. In this case, because we use the slope and y-intercept above, what I'm going to do is use the points that we have from our table. So I'll use red for this one over here. Actually, no, not red because we used it already. I'll use purple for the one over here. That's Hall A. So it has 0 people and 1,000. So that's this spot right here. Next, 25 and 2,000 people. So 25 and 2,000. Then I have 50 and 3,000. I'll zoom in here a bit. 75 and 4,000. And 100 and 5,000. So that's one linear equation graph. The second one that I'll use, it'll be green. That'll be for Hall B. Maybe I'll label it Hall A. And green will be Hall B. So remember, it had no initial value. So when 0 people went, 0 people were 0 cost. When 25 people went, it cost 15,000. When 50 people went, it cost 3,000. When 75 people went, it cost 44,500. And when 100 people went, it cost 6,000. So when I graph this line out for Hall B, I see that we have a point of intersection. The point of intersection happens to be at 50 and 3,000. So 50 is on the N axis and 3,000 is on the C axis. So what's significant at that point? Well, basically, when 50 people attend, cost is the same at both halls. That's when 50 people attend, right? Because remember, cost is along this axis here on the left. So when 50 people go, they're both the same cost. Both lines are at the same height. The significance happens is what happens on either side. So to the left of 50, that's when less than 50 people go. The green line is lower. It has a lower cost. So green is better. That's Hall B. Right? So for example, if 10 people went to the wedding, I see that Hall B would cost $500 and Hall C will cost somewhere around, looks like $1,400 or so. So much cheaper for B. What happens on the other side of 50? Well, that's where it changes. On the other side of 50, the purple line is lower, meaning that it has a lower cost compared to the Hall B. So Hall A is better. But at 50, that's where we break even. That's where both halls cost the same to us. So we don't care which one we go to. And that's solving linear systems by graphing. You put two lines on the grid and you find out where they intersect, because that's the solution to the two variables. There should always only be two variables. In this case, it was n and c. And the ones above were all x and y, only two variables, and we're trying to solve for x and y for those two variables. And that's linear systems, solving them by graphing. We're going to look at some other methods later on this chapter on how do we solve them without having to graph it, just by using algebra. But for now, that's graphing.